Hello everybody and welcome to chapter 4 of Advanced Functions. Today we'll be starting trigonometry, which is personally one of my favorite chapters. So to get started, today we're actually learning a completely new concept by the name of the radian measure. I will be explaining what this measurement is in the next slide, but overall today we'll be covering how to find the radian measure, how to convert between radians to degrees and degrees to radians, and lastly, just simple applications of the radian measure. Okay, so for the first half, we have how to find the radian measure. Well, so far you've been working with only degrees in trigonometry. However, this year you will learn the new measurement, which is called radians. So essentially, the radian measure can be found by the following. The radian measure of an angle theta is defined by the length A of the arc that subtends the angle divided by the radius r of the circle. If you're not sure what the subtends means, that means just like, I would say opposite. So you get your angle, for example, over here, right? So this arc over here will be what you're looking at. So again, this relationship is equals to theta, which is defined as in radians, not degrees. It has to be in radians, is equals to the arc divided by the radius. You could perform different little investigations, for example, like getting something circular and a piece of string and then keep finding the relationship between the arc and the radius and how that works out, but you don't have to do that because if you remember this relation, you'll always know what the radian is. So for example, if we want to actually define what a radian is, we know that for one complete revolution, the length of the arc equals to the circumference of the circle, which is of course 2 pi r. So we don't know what theta is yet, but we know that theta is equals to 2 pi r divided by r, which is the radius. Therefore, theta is equals to 2 pi. So from that, we know that one complete revolution measures 2 radians, which is always written as 2 pi rad, so rad instead of radians, just because it makes your life easier. So with this definition, you can now determine the relationship between radians and degrees. Honestly, it's much easier than you think. So first, let's talk about radius to degrees. Since we found out that the full revolution is equal to 2 pi radians, and we know that a full revolution in degrees is 360 degrees, then we could say that 2 pi radians is equals to 360 degrees. So from there, we can now freely convert between radians to degrees. So for example, let's find what 1 radian equals to. So to get 1 radian from 2 pi rad is equals to 360 degrees, we just divide both sides by 2 pi, right? So what we get is 2 pi divided by 2 pi, which is equals to 1. So 1 radian is equals to 360 divided by 2 pi. So that expression could be simplified further into 1 radian is equals to 180 divided by pi degrees. From here, we essentially found our key to converting between radians to degrees. Because now, whenever we see something in radians, we know that we could simply multiply it by 180 over pi degrees to find what it is actually in degrees. So for example, if we want to convert what pi over 6 rad is, then we simply have to multiply it by this value. So what do we get is that first we have pi times 180 divided by 6 times pi. Both the pi's just cancel out because we have a pi in the numerator and the denominator, which makes sense because we can't have pi's in degrees. So what we're left with is actually 180 divided by 6, which is 30. Thus, we found out that pi over 6 rad is actually equals to 30 degrees. So the most important takeaway from here is that you must remember to convert from radians to degrees, you simply multiply the radian measurement by 180 divided by pi degrees. Now, to convert from degrees to radians, you almost perform the exact same procedure, you just switch places between the degrees and the radians. So now we know that 360 degrees is equals to 2 pi rad. Now, instead of finding what 1 radian equals, we could find what 1 degree equals. So once we do that, or how we do that, is simply dividing both sides by 360 degrees. So 360 degrees divided by 360 degrees gets us to 1 degree. And then the second side would be 2 pi rad divided by 360, which could be simplified into 1 degree is equals to pi over 180 rad. Again, now we can convert from degrees to radians by simply multiplying any given value in degrees by pi over 180 radians. So for example, if you want to convert between 45 degrees to radians, we simply have to multiply this value by pi over 180. So what we get is 45 pi divided by 180. So if we simplify that, we actually get pi over 4. Therefore, 45 degrees is equals to pi over 4 radians. So all you have to remember for this part is, of course, to convert from radians to degrees, or sorry, from degrees to radians. See, I didn't even fix that. From degrees to radians. You must multiply the value by pi over 180. As you can see, these two are just reciprocals of each other, so if that helps you figure it out, then go for it. But I feel like just remembering this is simple enough. Now that we know how to work with the converting between radians and degrees, we could actually start applying what the radian measurement into other problems. So for example, as we discussed in slide 3, we were talking about how radians are the key part of the relationship theta is equals to the arc divided by the radius. As I said, this theta has to be in radians. Therefore, this is one of the biggest concepts you could apply it to. So here I brought out an example from the textbook, which was question 9, and it asked us the following. A circle of the radius 25 centimeters has a central angle of 4.75 radians. Determine the length of the arc that subtends this angle. Okay, so what we know from the question is that the radius is equals to 25 centimeters, and that theta is equals to 4.75 radians. So, plugging these values into the equation that we know, we get that 4.75 is equals to the arc divided by 25. So we just rearrange this and isolate for A, which would be 4.75 times 25 is equals to A. Therefore, A is equals to 118.75 centimeters. This is like one of the easiest application questions you could have. It's probably going to be knowledge, but again, you're just applying a concept. So there's another application question that I will now discuss with you. This one might seem a little bit complicated, but I can assure you it is so easy that you're just not going to believe it. So you will be asked to find the angular velocity of a rotating object. So again, hearing that might sound really complicated. It sounds extremely physicsy, you know? I don't personally enjoy physics that much, but again, math is just the whole application process over there. So here we are. For example, let's look at question 10. This dude rides his bike such that the back wheel rotates 10 times in 5 seconds. Determine the angular velocity of the wheel in A, degrees per second, and B, radians per second. So all we see is that the angular velocity is actually just the angle, so like a measurement per speed, you know? So we have degrees per second and radians per second. So let's do part A. We know that a full revolution in degrees is 360 degrees. We've been knowing this for years now, so it's nothing new. And so if he rotates that says G, come on Anna. If he rotates the back wheel 10 times, then the wheel has moved 360 times 10 degrees, right? In 5 seconds. If we want to find out what it is in 1 second, all we have to do is simply divide by 5, which is what I did here. I wrote it within the question, within the brackets, just because it's easier to simplify that way. Because you could just rewrite 10 over 5 as 2. So what we get is 360 times 2 degrees, which is 720 degrees per second. So that is our answer. I know the question seems a little bit difficult, but our answer is literally just converting into just degrees per second. Very difficult, I know. For the radians portion, we could do the exact same procedure. Just plug in the radians. So again, a 1 full revolution is 2 pi rad. So if he rotates 10 times, then it has moved 2 pi times 10 radians in 5 seconds. So in 1 second, we again divide by 5. We get 2 pi times 10 divided by 5 radians, which again could simplify to 2. So we get 2 pi times 2, which is equals to 4 pi rad per second. What you could also have done is again converted 720 degrees to radians by multiplying it by pi over 180, which you would see would get you exactly 4 pi. But depending on your teacher, perhaps they would want you to do the full procedure rather than converting, but again, they'll get you the same answer, so I don't really see a problem with it. Now, we have the homework for today, which is 6, 7, 8, 13, 14, 16, and 19. I will now show you some of those questions in the next little while. Okay, so for question 6, we're simply just approximating the radian measurement from each of the angles. So again, we just apply what we've learned, which is to convert from degrees to radians, you simply multiply everything by pi over 180. So that's it. That's all you do for this question. Just multiply everything by pi over 180. For 7, it wants you to convert to the exact degree measurement for everything. So now, again, you're just applying the knowledge you learned. And that means we're multiplying everything here by 180 over pi. Very, very difficult. Also, all the questions from 1 to 5 just let you learn that concept, so I don't know if you really want to do them. It's extra practice, but again, multiplication is not something you should be really focusing on learning. And that you should already know how to multiply numbers, so I didn't want to assign those. For 8, it's asking us to determine the approximate degree measure of all of these. So essentially, what it's saying here is that these measurements are actually it is also in radians, but it doesn't have pi. So again, you're just multiplying it by 180 over pi, and then you have to approximate because you're dividing by pi, which is an irrational number. So you'll have to just round it, for example, to 4 decimal places or 3 decimal places, whatever your teacher tells you to. Now, I've also assigned question 13. So question 13 talks about an aircraft and ships use nautical miles for measuring distances. At one time, a nautical mile was defined as 1 minute of arc, or 1/60 of a degree on the meridian of longitude following Earth's surface. As I told you before, my English isn't the best, so don't judge me. So what we have here is to determine the radian measure of one arc to 6 decimal places. So since we defined it as a 1/60th of a degree, to convert it to a radian, again, what we have to do is just multiply it by pi over 180, and we'll get our radian measure. The reason why it says 6 decimal places is because you get a really, really small number, and that number is approximately 0.000291. The radius of the Earth, for part B, is about 640 kilometers. Determine the length of the nautical mile using the old definition to the nearest meter. Okay, so the old definition, it was defined as... What is it defined as? It was defined as 1 minute of an arc, 1/60 of a degree along the meridian longitude. Okay, so all we have to do here is just convert it into using a radian measure that we found in part A. We're gonna multiply 6,400 kilometers. And what 6,400 kilometers is, that is 6,400,000. So we just multiply that by 0.000291, and we get approximately 1862, so 1,862 meters. For C, we're talking about the length of a nautical mile is no longer calculated this way, so everything you just done is completely useless, so I'm glad you did that. But in 1929, the International Extraordinary Hydrographic Conference adopted a new definition of exactly 1852 meters. So just the reason why using the radius of Earth might not be the best way to define the nautical mile. So this is not really a math question, this is more of just your logic behind the reasoning why it became 10 meters smaller. Personally, what I'm thinking is that since Earth is like spherical, we can't just use the radius at the largest or the biggest radius the Earth has, so right in the center at the equator. You also have to account for like the radius when it comes to like the polar ends. So I'm guessing that the average of those radii became smaller, and thus the nautical mile had to decrease as well. That's personally what I'm thinking. Now I've also assigned question 14. So a milliradian, so an mrad is 1,000th of a radian. Okay, milli, we know what that means, so we're good here. And milliradians are used in artillery to estimate the distance to a target. A. Show that the arc of length 1 subtends an angle 1 mrad at a distance of 1 kilometer. Okay, so what we know is that we're applying the equation from from slide 3, which is that theta is equals to the arc divided by the radius. So what we have here is that the arc is equals to 1 meter and the distance is equals to 1 kilometer, which is 1,000 meters. So A over R is actually 1 over 1,000th, which is 1/1000th of a radian. And since we have 1 mrad as an angle, we are correct, because that's what an mrad is defined as. For B, we're talking about a target scope shows that a target known to be 2 meters high subtends an angle of 0.25 mrad. How far away is the target in kilometers? Okay, so now what we're solving for is actually the radius, it seems like, because we're trying to find the distance between this, I'm guessing this is a sniper, and the target. So we are just rewriting the equation from slide 3 as R is equals to A over, or arc over theta. We know that theta is 0.25 and that the arc is 2 meters. Therefore, solving this, we just get 2 divided by 0.25, which actually gives us 8 kilometers as our answer. Now for the next question, we get 16. So 16 says the following. David made a swing for his niece Sarah using ropes 2.4 meters long, so that Sarah swings through the arc of length 1.2 meters. Determine the angle for which Sarah swings in both radians and degrees. Okay, so this is just a simple plug in the values into the equation. I think you could do this. So we're just doing 1.2 divided by 2.4, which is 0.5 radians. That's part A, or that's the radians portion. Then to convert it to degrees, since we can't just plug in the values, we're just multiplying our radian value by 180 degrees over pi, which is approximately 28.6 degrees. Very simple. As you can see, like this whole entire chapter is just focusing on the application of the 4 things I taught you. Lastly, I've assigned question 19, which is this wonderful problem over here. It's a little bit long, but It's nothing difficult. So 19. Satellites that are used for satellite television must stay over the same point of Earth at all times, so that receiving antenna is always pointed at the satellite. It is known as geostationary orbit and requires an orbit at a distance of approximately 35,900 kilometers above Earth's surface. So part A asks us to explain how a satellite could remain over the same point at Earth as it orbits the Earth. So this is just, again, just simple thinking. I would personally say that it must just follow the rotation of the Earth, so just rotate at the same time, just not go against it, for example, and not accelerate through it, just kind of vibe in there. For B, it's asking how long would such an orbit require for one complete revolution of Earth? So again, this is really simple. Let's think. The Earth is rotating, right, all the time, and that's how we get our 24-hour clock. So with 24 hours, we rotated once, therefore the orbit, such an orbit should also take 24 hours to rotate. Now for C, we're asked, what is the angular velocity of such a satellite in radians per second? Okay. So, since we're talking about an orbit, it's something spherical, so a full revolution is always 2 pi. Now, this is 2 pi per 24 hours. And since it's asking us per second, we're just gonna have to go down from hours to minutes to seconds. So what we get is 2 pi divided by 24, then divided by 60, and then again divided by 60, which would get us an approximate measurement of 0.0000023 pi radians per second. So it's a really, really small number, which is not surprising because Earth rotates pretty slowly. Now lastly, we have D. How does the angular velocity of the satellite compare to the angular velocity of the point on Earth that it is hovering over? Justify your answer. Okay, so as you discussed before, it must follow the rotation of the Earth, and it takes the exact same time. Then we found what its angular velocity is. If it wants to stay at the same place as the Earth, as the point on Earth, then it should be rotating at the exact same speed or at the exact same velocity. Therefore, it is the same. If it didn't travel at the same exact angular velocity, then it would just fly away from that point eventually. So that's about it. I don't think I've assigned another question, but overall you could go through all of these. They shouldn't take you very long. It's all either just converting from one measurement to another, applying the arcs, applying the angular velocity. Everything else is just a combination of the three, or like a combination of them. Or it just gives you, for example, a new definition and you just need to figure out how to work with it. For example, for 20, it's talking about, I don't know how to read it, grads. It's just another measurement that somebody tried to implement, but it never kind of took off. But you could learn how to use it here if you want to. Again, it's just going to be the exact same thing, just converting and learning a new measurement. But that's about it for the homework today. Okay, so with the homework done, I'd like to say thank you for listening to yet another chapter of advanced functions. I've noticed that I did a little bit of a goof for chapter 3. For example, I forgot to say in the very first presentation that you should always state your restrictions. So I made a little comment saying that you should do that. So hopefully those of you that are following or have just started to follow don't make that same mistake. Also for chapter 3.4, I have made a tiny correction onto these slides. So when you were solving equations, I like to personally get rid of the denominator, but that might get confusing for when you're solving inequality because you must keep the denominator there so you could see what factors are actually going into the final equation. So I would personally recommend to keep the denominator, even though that's not what I did. talk to your teacher about it, whatever way they explain to you, use that way. Otherwise, feel free to do the questions the way I did it. But yeah, that's about it for me today. I hope you had a lot of fun listening. See you next time.